Answering many questions in chemistry exams requires writing of electronic configuration of atoms. Therefore, writing electronic configuration of atoms both correctly and quickly is important in scoring more points and saving more time for focusing on other questions of exam. In this regard, I recommend my students that it is easily possible to obtain electronic configuration correctly and quickly by remembering 3 points and performing 3 steps. This is a method that I call it MSH method based on its 3 steps. This MSH method can quickly give us the electronic configuration of all elements that obey the Madelung rule, which are all of the main group or representative elements and most of transition and inner transition metals, together comprising 98, almost 100 elements of whole 118 approved chemical elements. To write the electronic configuration of 20 elements violating the Madelung rule, we should refer to tables or memorize them, as there is no method to obtain their exact electronic configuration analytically, although hopefully they just differ from the one based on the Madelung rule by having only 1 or 2 electrons moved from an expected atomic subshell to another one with a close energy level. To use the MSH method, 3 points or pieces of information should be remembered. The first point is the noble gases and their symbols and atomic numbers. There are 7 noble gases where in the order of increasing atomic number from the lowest one to the highest one. The first noble gas is helium with symbol He and atomic number 2. The second noble gas is neon with symbol Ne and atomic number 10. The third noble gas is argon with symbol Ar and atomic number 18. The fourth noble gas is krypton with symbol Kr and atomic number 36. The fifth noble gas is xenon with symbol Xe and atomic number 54. The sixth noble gas is radon with symbol Rn and atomic number 86. And finally, the seventh noble gas is oganesson with symbol Og and atomic number 118. The second point to remember is the atomic subshells that are filled between any 2 adjacent noble gases. This is simple to remember by considering that between the nth noble gas and its preceder, the atomic subshells Ns, N-2F, N-1D, and Np, if existed, are filled respectively. For example, xenon is the 5th noble gas, and between xenon and its preceder, krypton, the atomic subshells 5s, 5-2f or 3f, 5-1d or 4d, and 5p, if existed, are filled respectively. Where 3f doesn't exist, or we don't have any f subshell before 4f, so we can conclude that from krypton to xenon, the atomic subshells 5s, 4d, and 5p are filled respectively. Or in other words, when we build up electronic configuration of atoms by increasing atomic number 1 by 1, after passing krypton, at first electrons occupy the 5s subshell, then after complete filling of the 5s subshell, electrons enter the 4d subshell, then after complete filling of the 4d subshell, electrons enter the 5p subshell until it is completely filled too, and we reach xenon. So we see how it is possible to obtain type and order of subshells filled between any two adjacent noble gases simply by remembering the ns, n-2f, n-1d, and np sequence. This will give us that we have before helium the filling of 1s, between helium and neon the filling of 2s and 2p, between neon and argon the filling of 3s and 3p, between argon and krypton the filling of 4s, 3d, and 4p, between krypton and xenon the filling of 5s, 4d, and 5p, between xenon and radon the filling of 6s, 4f, 5d, and 6p, and finally between radon and oganesson the filling of 7s, 5f, 6d, and 7p, with the consideration that we don't have any p subshell before 2p, any d subshell before 3d, and any f subshell before 4f. The third thing to remember is the capacity of atomic subshells, or the maximum number of electrons that can occupy each kind of atomic subshells. Based on number of orbitals of each atomic subshell and the fact that each orbital, in accordance with the Pauli exclusion principle, can contain at most 2 electrons, capacities of atomic subshells are 2 electrons for each s subshell, 6 electrons for each p subshell, 10 electrons for each d subshell, and 14 electrons for each f subshell. So we have to move to the next subshell after putting 2 electrons in an s subshell, 6 electrons in a p subshell, 10 electrons in a d subshell, and 14 electrons in the case of an f subshell. To summarize and review, we should remember 3 points. The first one is all noble gases with their symbols and atomic numbers. The second one is the fact that when listed in the order of increasing atomic number from the lowest to the highest between the nth noble gas and its preceder, the subshells ns, n-2f, n-1d, and np, if existed, are filled respectively. And the third one is capacities of subshells, which are 2 for s, 6 for p, 10 for d, and 14 for f. By using mentioned points, we can perform 3 steps to obtain electronic configuration of any element that obeys the Madelung rule. The first step is to mark the 2 adjacent preceding and succeeding noble gases of the element of interest, or in other words, based on atomic numbers, we should find that the element of interest is between which 2 adjacent noble gases. The second step is to set the atomic subshells that come after the adjacent preceding noble gas by putting difference between number of electrons of the element of interest and its adjacent preceding noble gas in appropriate subshells with consideration of their order and capacity. In other words, in the second step, we determine the atomic number of the element of interest minus the atomic number of its adjacent preceding noble gas and put that number of electrons in the atomic subshells that are supposed to be filled between the 2 adjacent preceding and succeeding noble gases of the element of interest, while we also pay attention to order and capacity of the atomic subshells. Finally, the third step is to have all required things for the electronic configuration together in a correct manner. In other words, in the third step, we finally write the electronic configuration of the element of interest by putting the symbol of its adjacent preceding noble gas inside brackets and adding to it shorthand notations of subsequent occupied atomic subshells in the order of the principal quantum number or the Madelung rule, where shorthand notation of each occupied subshell consists of the numerical value of its principal quantum number beside the letter designation of its azimuthal quantum number with its number of electrons in the sub-level. That's all. The MS-Edge method. Mark the adjacent noble gases, set the subsequent atomic subshells, and have all together correctly. To demonstrate this MS-Edge method, we consider two examples. As the first example, consider acquisition of electronic configuration of the element sulfur with symbol S and atomic number 16. The first step is to mark adjacent noble gases, which are neon and argon in this case. The second step is to set the subsequent atomic subshells. Between argon as the third noble gas and its preceder neon, we have the filling of the atomic subshells 3s and 3p, which are supposed to have 6 electrons, in this case equal to atomic number of sulfur minus that of neon. Of these 6 electrons, at first 2 electrons are put in the 3s subshell to completely fill it, and then the remaining 4 electrons are put in the 3p subshell to give the electronic configuration of 3s2, 3p4 for the subsequent atomic subshells. Finally, the third step is to have all together correctly, which gives us neon 3s2, 3p4 as the electronic configuration of sulfur. As the second example, we consider obtaining of electronic configuration of the element lead with simple Pb and atomic number 82. The first step is to mark adjacent noble gases, which are xenon and radon in this case. The second step is to set the subsequent atomic subshells. Between radon as the sixth noble gas and its preceder, xenon, we have the filling of the atomic subshells 6s, 4f, 5d, and 6p respectively, which are supposed to have 82 atomic number of lead minus 54 atomic number of xenon equal to 28 electrons in this case. Of these 28 electrons, at first 2 electrons are put in the 6s subshell to completely fill it and give 6s2. Then 14 electrons are put in the 4f subshell to completely fill it and give 4f14. Then 10 electrons are put in the 5d subshell to completely fill it and give 5d10. Subsequently, the remaining 2 electrons are put in the 6p subshell to give 6p2. Finally, the third step is to have all together correctly, which gives us xenon 4f14, 5d10, 6s2, 6p2 as the electron configuration of lead. We discussed what MS-Edge method is and how it can be used. It is also good to pay attention to some other aspects of this method. As it can also be noticed in the previous examples, the first output of MSH method is the short form of electronic configuration, also known by other names like condensed electronic configuration. But MSH method can also be used to obtain the long form of electronic configuration by its stepwise implementation, where after the first output, the method is applied on the preceding noble gases until 1s2 or the electronic configuration of helium is reached. For example, the first output of method for lead was its condensed electronic configuration or xenon 4f14, 5d10, 6s2, 6p2. To acquire its long form, stepwise execution of method on the preceding noble gases can be used to obtain their electronic configurations as krypton 4d10, 5s2, 5p6 for xenon, argon 3d10, 4s2, 4p6 for krypton, neon 3s2, 3p6 for argon, helium 2s2, 2p6 for neon, and finally 1s2 for helium, where successive substitution of these from xenon to helium gives the long form of electronic configuration of lead as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2, 6p2. MSH method can also be used to obtain electronic configuration of monatomic cations or anions. This can be done directly or by acquisition of electronic configuration of neutral atoms at first and then changing its outer subshells by removal of electrons in the case of cations and addition of electrons in the case of anions, where number of electrons to be removed or added equals the absolute of charge number of ion. Here, any change in the order of filling of subshells, like swap between places of outer S and D subshells of cations of transition metals, should be taken into account. For example, to obtain electronic configuration of 2- monatomic anion of sulfur or S2-, either we can at first obtain electronic configuration of neutral sulfur atom with 16 electrons as neon 3s2, 3p4, and then add 2 extra electrons to get neon 3s2, 3p6 as the electronic configuration of S2-, or we can directly consider S2- with 18 electrons to get the same result. It is also important to mention that MSH method is closely related to the arrangement of common form of periodic table. Arrangement of common form of periodic table shows us that in the period n, the atomic subshells ns, n-2f, n-1d, and np, if existed, are filled respectively. And also the period n ends at the nth noble gas with the consideration that noble gases are ordered from the lowest atomic number to the highest one. For example, in the period 6, the atomic subshells 6s, 4f, 5d, and 6p are filled respectively. And the period 6 ends at the 6th noble gas radon. By considering this arrangement with the periodic table at hand, it is easy to obtain electronic configuration of atoms. For example, to obtain electronic configuration of lead, at first we find its position in the periodic table. Lead is located at the 6th period, in which the atomic subshells 6s, 4f, 5d, and 6p are filled respectively. And before their filling, the period 5 ends at the 5th noble gas, xenon. So we put the difference between number of electrons of lead and xenon in the atomic subshells 6s, 4f, 5d, and 6p with consideration of their order and capacity to get xenon 4f14, 5d10, 6s2, 6p2 as the electronic configuration of lead. As the example of lead also demonstrates, this periodic table method and MSH method are similar. But there is a big difference that MSH method doesn't require the periodic table to be at hand, which is a big deal. It is also important to consider that MSH method is based on the Madelung rule, and therefore it can't be used to obtain exact electronic configuration of elements violating the Madelung rule. 10 elements from the block D or transition metals and 10 elements from the block F or inner transition metals, together 20 elements, violate the Madelung rule by having 1 or 2 electrons moved from an expected atomic subshell to another subshell with a close energy level. Since there is no method that exactly determines which elements violate the Madelung rule and how they do so, we should refer to tables or memorize exceptions to be able to write exact electronic configuration of violating elements. Among famous ones are chromium with symbol Cr and the electronic configuration of argon 3d5 4s1 instead of argon 3d4 4s2. Copper with symbol Cu and the electronic configuration of argon 3d10 4s1 instead of argon 3d9 4s2. Palladium with symbol Pd and the electronic configuration of krypton 4d10 instead of krypton 4d8 5s2. Silver with symbol Ag and the electronic configuration of krypton 4d10 5s1 instead of krypton 4d9 5s2. Platinum with symbol Pt and the electronic configuration of xenon 4f14 5d9 6s1 instead of xenon 4f14 5d8 6s2. And gold with symbol Au and the electronic configuration of xenon 4f14 5d10 6s1 instead of xenon 4f14 5d9 6s2.